Picture a star system roughly 111 light years from Earth, still young enough that it hasn't finished settling into its final shape, surrounded by 3 concentric rings of leftover dust and rock, the raw material planets are built from. For years, astronomers studying that system noticed something odd. One of those 3 rings had a gap in it, a clean, empty lane cut through the debris, the unmistakable signature of something with real gravity sweeping a path through the material as it orbited. They had a strong suspicion about what was causing it. They just couldn't see it. Then, in the summer of 2025, using one of the most sensitive instruments ever built by human beings, they finally did. And what they found broke a record nobody had managed to break before: the faintest, lightest planet ever directly photographed outside our own solar system. This is the real story of TWA7b, and I want to start by clearing up something that's gotten muddled across a lot of the coverage of this discovery, because understanding what actually makes it significant requires understanding what it isn't. It isn't the first image ever taken of a planet beyond our solar system. Astronomers had been directly photographing exoplanets for close to 2 decades before this discovery, going back to the mid-2000s, using both ground-based observatories and the Hubble Space Telescope. It isn't even James Webb's first direct exoplanet image. That distinction belongs to a planet called HIP 65426b, a massive gas giant photographed back in September of 2022, only months after Webb became fully operational. So if this isn't the first image of an exoplanet, and it isn't even Webb's first exoplanet image, what actually makes TWA7b worth an entire video? The answer comes down to a distinction that sounds small, but is actually enormous once you understand the physics involved. Every direct image of an exoplanet before TWA7b, including Webb's own earlier picture of HIP 65426, was a photograph of a planet astronomers already knew existed, typically found years earlier through some other method, then simply photographed afterward once the right instrument became available. TWA7b was different. It was the very first time James Webb, or arguably any space telescope, discovered a completely new, previously unknown planet purely through the act of direct imaging itself, finding something nobody knew was there simply by looking hard enough, in exactly the right way, at exactly the right target. Let's talk about why that's so difficult, because the difficulty is really the whole story here. Stars are almost incomprehensibly bright compared to the planets orbiting them. Our own sun, for comparison, outshines even a large planet like Jupiter by a factor of roughly 1 billion. Trying to directly photograph a planet next to its star is a bit like trying to photograph a firefly hovering directly in front of a lighthouse beam from several miles away, except the actual brightness difference involved is usually even more extreme than that comparison suggests. For most of the history of exoplanet astronomy, this made direct imaging almost entirely impractical, except in the most favorable unusual circumstances, typically involving enormous planets. Several times the mass of Jupiter sitting unusually far from their star and still glowing with residual heat left over from their own relatively recent formation. Webb's specific advantage lies in a piece of hardware called a coronagraph, installed on its mid-infrared instrument, known by the shorthand MIRI. A coronagraph works by physically blocking out the light from a bright central object, in this case a star, allowing much fainter light from anything nearby to actually become detectable. The same basic principle behind holding your hand up to block direct sunlight so you can see something dim standing just beside it. The specific coronagraph used to find TWA7b was developed in France, and researchers led by astronomer Anne-Marie Lagrange at the Centre National de la Recherche Scientifique in Paris used it to achieve something genuinely unprecedented, suppressing the light of the host star enough to detect a planet roughly 100,000 times fainter than that star itself. Now let's talk about the planet they actually found, because the numbers here matter enormously to understanding why this discovery landed the way it did in the scientific community. TWA7b has an estimated mass of around 100 times that of Earth, comparable in scale to Saturn, or roughly 1/3 the mass of Jupiter. On its own, that's a fairly ordinary planetary mass, nothing shocking by exoplanet standards generally. What made it remarkable is the comparison to everything that had come before it. TWA7b is roughly 10 times lighter than any previously directly imaged exoplanet, making it, by a wide margin, the lightest, faintest planet ever successfully photographed outside our solar system. Every single direct image captured before this one involved a considerably larger, brighter world, simply because anything smaller had always been considered essentially undetectable using existing instruments and techniques. That gap matters because it represents something more than just one interesting data point. It represents a demonstrated capability, proof that direct imaging technology has advanced enough to start reaching down into a whole new category of smaller, fainter planets that were previously completely invisible to this particular method. Researchers studying exoplanets have spent years pointing out that direct imaging, for all its scientific value, was fundamentally biased toward finding only the largest, most extreme worlds, missing entirely the smaller, more numerous, and arguably more interesting planets that make up the bulk of what we now know exists throughout the galaxy. TWA7b is the first concrete evidence that this bias is starting to break down. Now let's go back to that gap in the debris disk, because it's actually central to how this discovery came together, and it reflects a genuinely elegant piece of detective work. The star TWA7 is surrounded by 3 concentric rings of dust and small rocky debris, material left over from the same process that formed the star itself and any planets orbiting it. Astronomers had already noticed, well before this discovery, that one of those 3 rings had a distinct, visible gap carved into it, and based on decades of studying how planets interact gravitationally with surrounding debris, they had a strong working theory that an unseen planet, sweeping up or scattering material as it continued orbiting the same lane of space, was most likely responsible. This kind of indirect evidence, gaps in structures visible in debris disks around other young stars, has actually been used for years as a way of predicting where hidden planets might exist, long before any instrument capable of directly confirming those predictions became available. Multiple other young star systems studied by Hubble and various ground-based telescopes have shown similar telltale gaps, each one essentially a placeholder marking where astronomers suspected, but couldn't yet prove, a planet was hiding. When Webb's coronagraph finally captured TWA7b sitting almost exactly within that predicted gap, roughly 52 times farther from its star than Earth sits from our own sun, it did something more than simply add a new planet to the catalog. It validated an entire predictive method, confirming that these visible gaps really do reliably mark the presence of genuine, physically real planets, exactly as researchers had theorized. There's a specific reason TWA7 made such a promising target for this kind of search in the first place, and it has to do with the broader neighborhood the star belongs to. TWA7 is a member of what astronomers call the TW Hydrae Association, a loosely bound group of young stars that all form together from the same original cloud of gas and dust, and that consequently share a remarkably similar age, estimated at somewhere between 6 and 10 million years old. Because every star in this association formed at roughly the same time, astronomers have unusually precise, well-constrained estimates for exactly how old TWA7 actually is, far more precise than what's typically available for an isolated star with no known stellar siblings to compare it against. That precision mattered directly to this specific discovery, because a planet's brightness and temperature both depend heavily on how much time has passed since its formation, with younger planets generally running hotter and brighter as they slowly radiate away the leftover heat from their own creation. Having a confident, well-established age for the host star let researchers make far more accurate predictions about what a genuine young planet orbiting it should actually look like, making it considerably easier to distinguish a real detection from background noise or contamination. Based on the observations researchers actually captured, TWA7b appears to have a surface temperature somewhere around 120 degrees Fahrenheit, a notably warm reading for a planet sitting so far from its star, and one consistent with a young world still glowing from its own relatively recent formation, rather than having had enough time to cool down toward equilibrium with the cold surrounding environment of deep space. I want to spend a moment on the honest, careful way this discovery was actually reported, because I think it says something important about how real science operates, separate from how these stories often get repackaged for headlines. The research team behind this discovery, publishing their findings in the prestigious journal Nature in June of 2025, was explicit about the fact that TWA7b's status as a genuine planet, while very strongly supported by the evidence, isn't stated with total, absolute certainty. Researchers calculated a small, specific probability, roughly 0, 34%, that the faint infrared source they detected could actually be an unrelated background galaxy, its light merely happening to align with almost exactly the same position in the sky, as seen from Earth, without any genuine physical connection to the TWA7 system at all. That's a genuinely small chance, well under 0.5%, and multiple independent lines of evidence, its position precisely within the predicted disk gap, its brightness and color matching theoretical predictions for a young planet of this specific age and mass, and its consistency across multiple observed wavelengths all support the planetary interpretation strongly. But the researchers chose honesty over overstatement, explicitly flagging the remaining uncertainty rather than declaring unconditional absolute proof before every possible alternative explanation had been fully ruled out through additional follow-up observation. That kind of careful hedging isn't a weakness. It's actually one of the clearest signs of legitimate, trustworthy science at work. Astronomy has a long history of promising, exciting signals that later turned out to be something far more mundane, background objects, instrumental glitches, or statistical flukes that happen to look meaningful at first glance. Building that same skepticism directly into a landmark discovery, rather than only applying it after the fact once doubts start to surface, is exactly the kind of rigor that gives a finding real, lasting scientific weight, instead of a headline that eventually has to be quietly walked back. It's worth zooming out and asking why any of this actually matters beyond the technical achievement itself, because the answer connects to some of the biggest, most fundamental questions in modern astronomy. As of this discovery's publication, astronomers had confirmed nearly 6,000 exoplanets scattered throughout the galaxy, and the overwhelming majority of them were found using indirect methods entirely, watching for the tiny telltale dimming of a star's light as a planet passes directly in front of it from Earth's specific vantage point, a technique called the transit method, or measuring the subtle gravitational wobble a planet's mass induces in its host star's position and velocity, known as the radial velocity method. Both approaches have been extraordinarily productive, responsible for the vast majority of exoplanet discoveries made to date, but both come with real, inherent limitations. The transit method only works at all if a planet's orbit happens to be aligned in exactly the right way to physically pass between its star and Earth, meaning it systematically misses an enormous number of planetary systems oriented differently relative to us, regardless of how many planets they might actually contain. The radial velocity method tends to work best for large, massive planets orbiting relatively close to their star, since those produce the strongest, most easily measurable gravitational tug. Direct imaging sidesteps both of those specific limitations, at least in principle, capable of detecting a planet regardless of its particular orbital alignment relative to Earth, provided the planet itself is bright enough and sits far enough from its star's overwhelming glare for a coronagraph to actually separate the two. The trade-off has always been technical difficulty, requiring exactly the kind of extreme light suppression technology TWA-7b's discovery finally demonstrated, working at a genuinely new, more sensitive threshold. And unlike a transit or a radial velocity measurement, which give astronomers useful but fundamentally indirect mathematical signatures, a direct image gives researchers an actual physical target, something they can continue observing and re-observing across different wavelengths and extended periods of time, gradually building up a genuinely richer picture of the planet's temperature, its atmosphere, and its composition in a way indirect detection methods alone simply cannot match. There's also something worth appreciating about what a system like TWA-7 actually represents scientifically, beyond the specific planet found within it. Because the star is still young, its surrounding planetary system hasn't yet finished forming and settling into whatever final stable configuration it will eventually reach. Studying a system caught at exactly this formative stage gives researchers something close to a genuine observable snapshot of the same basic process that once built our own solar system billions of years ago, long before Earth or any of its neighboring planets had finished taking their current familiar shape. That's an opportunity indirect detection methods, however productive they've been at simply counting and cataloging distant worlds, generally can't provide in nearly the same depth or detail. So here's what I actually want you to take away from all of this. TWA-7b isn't remarkable because it's the first picture ever taken of a planet outside our solar system. It's remarkable because it represents the first time James Webb, using one of the most sensitive coronagraphs ever built, found a genuinely new planet through direct imaging alone, a world roughly 10 times fainter and lighter than anything ever successfully photographed this way before, sitting exactly where earlier, indirect evidence had predicted an unseen planet should be. It's a discovery built on years of careful engineering, patient theoretical prediction, and honest, appropriately cautious scientific reporting. The kind of real, hard-won progress that rarely makes for a clean, simple headline, but that actually moves an entire field of astronomy meaningfully forward. If you want to know what comes next for TWA-7b, whether researchers eventually confirm its orbital motion definitively or manage to extract real details about its atmosphere through follow-up observation, subscribe and turn on notifications, because this is exactly the kind of ongoing research Webb was specifically built to carry out over the coming years. And drop a comment telling me whether you think this new leap in sensitivity means astronomers are getting genuinely close to directly imaging a small, rocky, Earth-sized world someday. Because after seeing exactly how much smaller and fainter TWA-7b is compared to every previous direct image, I think the particular milestone just moved a lot closer than most people probably realize.